We've already in the past found the area between a function and the x-axis between two boundaries. But sometimes we have more than one function involved. For instance, if I had, say that is function f, and this is function g, and I want to find this area between those two functions.
Oh my gosh, I already used up my whole spec.
You need some paper?
All right. Any idea of how I could find the area between f and g?
Take the area of F and then subtract that, or subtract from that the area of G.
Okay, if we take the area of f, the upper function, and subtract the area of the lower function, that should leave us with the shaded region. Really, what we're thinking about doing is if we have little rectangular strips in between the two functions, remember when we first found area, we found the area of the rectangles, we did a Riemann sum. This is the same idea. We've got, and I'm drawing the rectangular strips for a reason, because in a few minutes we'll have some horizontal strips. But if you have rectangular strips, then that means your functions are going to be in x. And to find the area between f and g, we're going to integrate, say we're going from a to b. So if we're just going from a to b, that's what we want, just from a to b. And I'll erase this if I can. So that's the only area that I want to find, between a and b, between those two curves. So it's a good idea to draw the functions or look at the functions, because you've got to figure out which function is the upper function and which function is the lower function. So in order to find the area between f and g, we take f of x minus g of x. And we integrate. So it's not a difficult thing to do. Sometimes we'll have to find our limits of integration. Sometimes they'll be given to us. So we're going to look at some different examples today. Sometimes where they're given, sometimes where we find them. But basically, it's the upper function minus the lower function. So it's just one of those things that when you see it, it makes pretty much sense that that's how you do it, since you already know how to find the area between the curves. So let's just look at an example. I want to find the area of the region that's bounded by y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So it's a good idea to graph it. This is one you would probably not have your calculators available to you if you had one this simple on the test. Because these are functions that we can graph pretty easily. If we graph y equals negative x, well, that's just a slope of negative 1, and it's just going to look like this. And it's hard to sometimes graph just right on this. So there's y equals negative x. If I graph y equals x squared plus 2, well, that is just a parabola that's shifted up 2 units. So it's easy to see which is the upper function and which is the lower function. And now I am going between x equals 0 and x equals 1. So if we were to look at the area, that's the area that we're looking for.
And is this what you said, where you can have horizontal?
Now this is going to be vertical strips.
Okay.
We use horizontal strips if you have a function that's in y that's not easy to change to x. So, and we'll see an example of those in a minute. So, which is the upper function?
Y equals x squared plus 2.
X squared plus 2. So we are going to integrate this function from 0 to 1. Don't forget your limits of integration. You always want to put your limits. And we're going to do x squared plus 2 minus a negative x. So it's probably going to be easier if we go ahead and simplify that before we integrate it. So we'll have x squared plus x plus 2, and no, you don't have to reorder it. I just did it because I'm a math teacher and I like things to be in order, but it's not necessary. But you do want to do your minus the negative. So parentheses are sometimes very important when you're subtracting because you always have to distribute that minus math stuff. So if we integrate here, what are we going to get?
X cubed over 3 plus x squared over 2 plus 2x
That's it.
evaluated at 1 and 0.
I love it when we evaluate at 0.
True.
Because then all we have to do is plug in our 1. So we're going to have 1/3 plus 1/2 plus 2. And so that's 2/6 plus 3/6 plus 12/6, which is 17/6. If you couldn't use a calculator, I would expect to see the 17/6. I'm getting a look over there, so let me pause it. Okay, in the last example, we were given some limits. Those graphs didn't intersect, but sometimes you're going to have graphs that do intersect. And if your graphs intersect and you are not given limits, then you need to find those intersection points. So if we have f of x equals 2 minus x squared, and g of x is x. Again, this one's pretty easy to graph. 2 minus x squared just means that that's the parabola flipped upside down. So it's going to look something like this. And y equals x is going to look something like this. And so the area that we're looking for is from here to here. So how do I figure out what those intersection points are?
I'll get a new calculator.
No,
You have to,
because this would probably be a non-calculator.
No.
Oh, what do we do?
Oh, would you
You
take the derivative and set it equal to 0? No.
No, you just set them both equal to each other.
Set them equal to each other.
I did.
Find out where they have the same value. So 2 minus x squared equals x. And I'm going to go this way. X squared plus x minus 2. Factor. So x can be -2, or x is 1. See, because I drew this, I wouldn't really, and I didn't have a graph, I really wouldn't be able to tell exactly where they're intersected unless I actually set those functions equal to each other. So our limits are what?
-2.
-2 and 1.
-2 and 1. Now, which function's the upper function?
The 2 minus x squared.
Okay, f of x is the upper function. So we're going to have our 2 minus x squared minus x dx. Okay, so go ahead and integrate that and see what that area is. We all got the right function. What did you get when you integrate?
2x minus x cubed over 3 minus
1/3
x.
x
It's like,
That's the same thing. as
Minus,
Oh, x cubed over 2. I didn't hear the 3 part. Yeah, no, just say that. Minus x squared over 2.
so what do you get when you plug in a 1?
1 minus
2.
1/3 minus 1/2.
How about 2 minus
2
1/3
minus 1/3
minus 1/2?
Minus 1/2.
I mean, yeah, that works.
That's what I got.
I'm glad that works. 2 minus 1/3 minus 1/2
Mm-hmm.
minus
4.
Oh.
-4
Found my problem.
plus 8/3 minus 2.
Yes, so the 2's cancel out.
It would still be -2.
16 is 47.
Yes. All right, so here we have 12/6 minus 2/6, 10/6 minus 3/6 is 7/6
Raised to the negative. Oh, that's
minus -6 plus 8/3. That's negative 18/3 plus 8/3 is negative 10/3. Wait, I did something wrong. -4 plus 8/3 minus 2. Maybe it was over here. 12/6 minus 2/6.
I got 35 over 6.
No, that'll be right
Did-
because then you'll add the 7/6.
Minus 3/6.
It's your -2.
Okay,
It's supposed to be a +2.
no, it's negative.
Okay.
So we have minus a -4.
Oh, what's that?
This would be 4 divided by 2 is 2, plus 8/3. Okay, so this is negative 10/3. Oh, okay. That may be my problem. Is 7/6 plus 26, that was it, which is 27/6, which is 9/2.
What? Got 35 over 6.
Okay, we're looking at the sine of x and the cosine of x. We saw that there are several regions that have an equal area, and we are looking at the shaded area and we have to determine where those are equal. We said that the sine of x and the cosine of x are both positive in the first quadrant, and they're both negative in the third quadrant. So that sets up our limits of integration. In the region that we're looking at, even though they don't look like it, all of these regions have the same area. In this particular region, the sine of x is above the cosine of x. So we're integrating that.
Write it like that.
Okay, so we've got a negative
And then it's
cosine of x minus the sine of x. And it's, I think, gentlemen, I think it's easier if we'll pull out that negative.
a great high five.
I believe your calculations would be easier. All right, so if we do that,
2 squared root of 2?
what's the cosine of 5 pi over 4?
Negative square root 2 or 2.
And the sine of 5 pi over 4?
Negative square root of 2 over 2.
See, she's on mine.
Minus the cosine of pi over 4 plus the sine.
Doesn't even let us say it this time.
That one's so easy.
That hurts.
So here we have the opposite of negative 2 square roots of 2 over 2 minus 2 square roots of 2 over 2, which is the opposite of negative 2 square roots of 2, which is 2 square roots of 2. Now we should expect to get a positive number because you're looking for the area between the two curves, so we should expect to get a positive number.
Yes.
Functions that we're going to look at intersect more than once or more than 2 points, and we're going to have to find all those points of intersection. So if we have the function f of x equals 3x cubed minus x squared minus 10x, and g of x equals negative x squared plus 2x. Now, we're going to work through this like we don't have a calculator available because this is a simple enough function we could figure out what's going on here. When you have a cubic function and the leading coefficient is 3, your end behavior, if it's a positive leading coefficient and an odd function, your end behavior is like this. Think about what x cubed looks like. If it were negative, those would reverse. All right, on the second function, because it's a negative x squared, we know our end behavior is going to look like this. And I just do that so we get an idea of what that function could look like. Now, if we kind of graph the function before we find the points of intersection, what I want to do is find the zeros of each function. So for f of x, I'm going to factor out an x, and we'll have 3x squared minus x minus 10. And I think I can factor if I do a 2 and a 5, that's going to give me 10. And if I have that one negative and that positive, does that work?
Yes.
Okay.
Yes.
So x could be 0, that's a 0. X equals negative 5/3, and x equals 2. Those are my zeros. That's the grown-up method of factoring.
Well, I was never taught it, so I'm just a kid.
Yep, you got that right.
Yeah, well,
Was that negative 5 then?
I didn't
Yes.
use sarcasm.
All right, so we're going to have an intersection here, here, and that's not quite negative 2, right there. So if the end behavior is this way and this way, I don't know exactly what it's going to look like, but it's going to look something like this. I just need an idea. Something like that. Don't really care exactly how high it is. Now the other one is a parabola. For g of x, I'm going to factor out a negative x, and we will have x minus 2. So x is 0, and x is 2. So those are the zeros for g of x. And g of x is going to look something like this. And down here somewhere, they're going to intersect again. So we've got to figure out where they intersect. We've already found 2 intersection points because they have the same zeros. How do I get that third intersection point?
Set them equal to
Set them equal to each other. So 3x cubed minus x squared minus 10x equals negative x squared plus 2x. Well, those cancel. And we'll have 3x cubed minus 12x. So factor out an x, a 3x, and we get x squared minus 4. We get x is 0, and x equals plus or minus 2. Now remember, I haven't drawn this to scale. So right here when x is 2 is where they also intersect.
Okay, that line is
Okay. Now, what happens when we go from negative 2 to 0? Which function's on top?
The f of x.
F of x. But when we go from 0 to 2, which function's on top?
G of x.
So we have to do 2 separate integrals here.
It's not even nice.
Because we've got f of x on top here, but g of x on top here.
So the first one is like the integral from negative 2 to 0 of the g of x, the f of x minus the g of x.
Negative 2 to 0 of f of x minus g of x plus from 0 to 2 of g of x minus f of x. If we don't do that in order, you'll get the wrong answer. No, if you go all the way from negative 2 to 2, it's going to be wrong. You have to look at where things switch.
Okay, please don't.
All right, so take a few minutes and let's see if you can get that. We get for our function here? What's your function? Once you
Three.
integrate?
3/4 x to the fourth minus 6x squared. Plus,
Is that all on that? Okay.
that's
Yeah.
on that one, and then plus negative 3/4 x to the fourth plus 6x squared evaluated at 0 and 2.
Agreed.
All right.
Where did you put 6?
How are you there?
Oh,
Okay.
because you did,
I mean, is everybody okay? You're not okay with that?
because when you integrated that, the 12x, when you, about the 12x, you kept the 12 and then it's x squared over 2,
What 12x?
the one from the problem.
And over here you have negative x squared plus 2x minus 3x cubed plus x squared plus 10x. So you have to combine
Okay.
and then integrate. So Joe, did you get that far?
I did get that far, but I screwed up.
Do you see where you messed up? Okay. Joshine, you okay?
If we
Yes.
didn't put everything together and we kept them as,
Oh, you make it a lot harder,
okay.
Yeah, that
a lot harder.
And then
So-
putting in 0 for everything.
So don't forget, it's 0 minus,
Yeah,
and you get a 12 here.
so you get minus 12 plus 24.
You get that negative. So,
Plus, and I think this is 24 minus 12. So 12 plus 12 is 24. Right. We'll do the horizontal strips tomorrow. Your assignment is on page
That was the assignment.
4. I can't read the board.
You need reading glasses.
418, I believe. Yes,
That's today.
5,
During advisory?
9, and 21 to 30 every third.
During advisory?
That's not very many problems.
Everybody vote for Grace Nay.
So
Can we
please
vote?
do these problems.
I loved her.